Okay, in this lesson, now we're going to dig into center of mass a little bit and get a formal definition, as well as conceptually how to think about center of mass, and that is where we're starting. Conceptually, how should we be thinking about center of mass? Well, the first thing that I want you to think about when you think about center of mass point is that it is always nature's balance point. So in other words, we, me, you, all of us, are a system of particles. We have a head, arms, hands, a torso, legs, feet. We could break it down even further. We're made up of many particles, billions of particles if you're talking about at the molecular level. The center of mass point will always be what I think of as that seesaw point where the seesaw is in perfect balance. So in other words, if I flash froze you, so I had you strike your very relaxed pose that I have shown here, and I flash froze you, and then I put a wedge underneath you until I balanced the left, right, that kind of seesaw tip balance. The point where you would balance, that is the center of mass point. For you, it is the center of mass point for any object. Any object's balance point will be the center of mass point. And it's not a coincidence, by the way, that our center of mass point is up somewhere near our heart. So our heart is distributing blood throughout our body, very close to the center of mass point. Okay, second thing conceptually, where I want your neurons bending towards, is the fact that the center of mass point is also nature's natural point for rotation. Okay, well, and I'll explain what I mean by nature's natural point for rotation. So if I have two objects, let's say I have a big object, object 2 here, and I glue it to a small object, object 1 here, with like a really light, really strong bar. Okay? Now, my center of mass point will be the seesaw balance point, but also if I wanted to spin it, it turns out that spinning, the effort it would take for me to spin the object is always the least amount of effort if it spins about the center of mass point. Now, I could take a peg, right, and like peg the object anywhere and like pin it here and then spin it, but that takes more effort. And anywhere I peg the system down that is not the center of mass point, it takes more effort than the center of mass point. So it is nature's natural point of rotation. And here I kind of have my last point and that rotation concept combined into one. So if we consider that it's nature's point of rotation, if you were flying through the air, tumbling about, you would be rotating about your center of mass point. So you get like this type of rotation. But your center of mass point, if I could laser beam spot it, would follow the exact projectile motion that a point would follow. So if I wanted to make you a point particle, I would put that point particle at the center of mass point, and that center of mass point would follow the same path as the point would follow if I were to actually make you a point particle. So that is how I want you to think of center of mass, and I do want you to think of center of mass that way really before getting into the numerical calculations, and that's the next part of this lesson here, the numerical calculation. So we have the formal mathematical definition for center of mass right here. The center of mass is going to be a position from 0, 0. So that's the R vector from 0, 0 to the center of mass point. So that's going to be like the R vector here. So that's going to be the R vector to the center of mass point. Will be given by taking mass 1, which may be our head times the position vector to our head, mass to our torso times the vector to our torso, adding all those up and then dividing by the total mass. And then if we want the velocity of the center of mass, we're going to throw our calculus into action here. So we're going to take the derivative of the position vector to get the velocity vector, and the velocity vector is m1v1 plus m2v2 plus m3v3 divided by the total mass. We'll again throw our calculus into action here to get the acceleration is the derivative of the velocity vector. To get the acceleration of the center of mass is m1a1, m2a2, dot, 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 over the total mass. And voila, we get back to sum of the forces external equals the total mass divided by the acceleration of the center of mass. Notice that capital M that I have here will cancel with the capital M down here that we're going to get. So the equation that we had at the bottom of our last page of notes, I can go back to that quickly. Look, it's the same equation. Physics is nothing if not consistent and logical. So the theoretical notion of how to think about center of mass as being, the balance point, point for rotation, and the point particle path point, if we were to kind of laser beam it out, I definitely need you to focus on really in every problem. This formal definition, we're not going to have to focus on so much as a formal definition. We're going to use a specific example in our next lesson, our next page of notes, to see how numerically this plays out, and that'll give you a better way to think mathematically about it than I think just looking at the formal definitions.